Welcome back to solving logs, equations, and inequalities. We're going to review when we have to use the technique of condensing. Condensing takes two separate logs, as in these cases here where I'm underlining, and rewrites them as a single log. If the operation between the two logs is addition, then you're going to want to multiply your of the numbers together. If your operation between the two logs is subtraction, then you're going to want to make a ratio out of these two of the numbers. So let's get started. In both of these cases, we're going to condense down to a single log, which means then we're going to rewrite them as an exponential expression. So this log on the left-hand side becomes log base 3 of the number 6x equals the exponent 3. I now rewrite as exponential, and I get the of the number x is equal to the base 3 raised to the third power. When I solve, I get 6x is equal to 27 over 6, or 27. X is equal to 27 over 6, which is equal to, divide by 3, 9 over 2, or 4.5. In example number 2, even though I have the natural log, which is in base E, my properties for condensing and expanding still apply. So I have log, the natural log, let me write it as ln, the natural log of 18 over 3x is less than 2. Remember, this is ln means we're in base E. So I get the of the number 18 over 3x is less than base E raised to the second power. This E comes out of the ln, that is log base E. Now I'm going to reduce and solve, and that becomes 6. And I have 6 over x is less than e squared. X is greater than 6 divided by e squared. So over here I have x is greater than 0.8120, which if you wrote it in interval notation would be this number going on to infinity. I don't have room for that here. I'll write it over here. 0.8120 to infinity, positive infinity. Originally, our problem was expressed as a less than, so we have to be careful of at lower limit. X has to be greater than 0, and in fact, all of our solutions are. So we are good to go and can stop right there. This, through the process of solving, it now became a greater than. We're going to keep condensing, but this time we're going to end up with a log on both sides, which means that I'm going to work with the of the number pieces of the logs and set them equal or unequal according to the problem. I'm going to condense this power, coefficient to a power, and condense the two logs all at once, and so I get log base 6 of the number 0.1x squared is less than log base 6 of the number 10. I multiplied these two together, and I multiplied these two together after I put the power on it. My of the numbers have to be unequal then, So 0.1x squared has to be less than 10. And x squared has to be less than 100. And x has to be less than plus or minus 10. Negative 10 doesn't work. So I have x is less than 10. And then I have to check my lower limit. And this second term here said that x had to be greater than 0. So in interval notation, it looks like that. 0, 10, both with parentheses. I apply the same properties and rules when I'm condensing natural log. Remember, we are in base E with a natural log. When I condense, I get ln of 64 divided by 8/3 is equal to ln of 4p. I'm solving for p. The thing to remember is, number one, that our of the numbers have to be equal to each other, and division by a number is the same as multiplication by its reciprocal. So 64 times 3/8 is equal to 24 equals 4p, and 6 equals p. And there is our answer. The next slide, what we're going to do is we're going to expand. And I want to draw your attention that they give us these decimal approximations. To some logs, and we're going to use those. We could use change of base formula, but we want to practice expanding, so we're going to do that with these numbers. And we're going to start with log base 2 of the number 125, which I don't have a decimal approximation, so I'm going to write it as log base 2 of the number 5 cubed, and I chose 5 because I have a decimal approximation for that of the number. Then I'm going to pull my power down to the front, and then I'm going to substitute in the decimal approximation. So that becomes 3 times 2.3219, which is about 6.9657. Moving on to problem 2, I'm going to take and rewrite 70. I know that that can be log base 2 of 7 times 10, but 10 is 2 times 5. So 7 times 5 times 2. And I can write that as a sum of those 3 logs. Log base 2 of 7 plus log base 2 of 5 plus log base 2 of 2. Now notice that I have a remember up here that log base b of a matching number b is equal to 1. As long as these two match, then it equals 1. So that means log base 2 of the number 2 has to equal 1. So I'm going to substitute in the decimal approximations, and I get 2.8074 plus 2.3219 plus 1. And when I add those together, I get an approximation of 6.1293. Last problem that we're going to do, this is log base 2 of the number 49 over 5. And I'm going to split that up. log base 2 of the number 49 minus log base 2 of the number 5. I'm going to recognize that 49 is 7 squared, and so I get 2 log 2 base 2 of the number 7 minus log base 2 of the number 5. Plug in my decimal approximations. 2 times 2.8074 minus 2.3219, and when I do that I get the approximate value of 3.2929. Okay, all right, you should be able to try a couple of these problems. 10 and 18. If you are still in your pods and you're not doing this at home, go ahead and work with your in your pods. And if you are at home and you have questions, email me. Thanks. I'll talk to you tomorrow. Bye.